All right, today we're going to take a look at non-terminating decimals, specifically at repeating decimals. So do you remember when we said that a fraction could be written as a terminating decimal? In the denominator, yeah. So we said something like, this was in Theorem 7.1. Said if the, I'm going to add one word in here that we didn't mention, that it's the simplified fraction, right? We have to look at if there's an ability to reduce. The simplified fractions denominator contained only factors of 2 and or 5. So if we could break it down, simplify it, and the denominator only had 2's and 5's, or only 2's or only 5's, then it would be a terminating decimal. So what would it mean if it cannot be written as a terminating decimal? Well, if the fraction cannot be written as a terminating decimal, this happens if, or when that can't happen, then if the fraction is an integer over an integer, so we're still working with integers on top and bottom, integer over an integer, and does not terminate, then it will repeat. So we're going to do one that has that property next, and identify the point at which it repeats and how we can see the point at which it's repeating quickly. So our fraction is 1 over 24. And we're going to show it out longhand. So we do the 24 on the outside and the 1 underneath. So clearly 24 goes into 1 0 times. So we put a decimal place and another 0. Move the decimal up. The 24 goes into 10, another 0 times, right? Okay, everybody good so far? All right. So I need a third 0. Now I have the number 100. How many 24s are there in the number 100? There are 4. And what is 4 times 24? 96 is correct. And we will subtract. So I'm okay if you grab your calculator, do the quick multiplication stuff. You're just going to show the division parts here by hand. So what is 100 minus 96? 4. And we would bring a 0 from the top down again. So now I have 40. So how many 24s are there in 40? 1. 1 times 24 is 24, and we subtract, which leaves us with 16. Okay, well 24 doesn't go into 16, so we're still on the right track. Put another 0. How many 24s are there in 160? There are 6. Yes, indeed. So 6 times 24 is 144. And what do you get when you subtract? 16. So if you don't notice it at this point and you do one more step, you will notice it quickly. But at the point when the subtraction gives you the same thing you've seen before in any step, it means you've found a repeat. Here, what happens is that the repeat's immediate. Right, we went from 16 to another remainder of 16, and we will keep getting remainders of 16 forevermore. So the number that's actually repeating is only the last number because I continue to get those 6's showing back up again. So my decimal is 0.0416 with the with the bar only over the 6. So this type of a decimal is a repeating decimal. And the part that repeats at the end, in that case the 6, is called the repeat end. And I've got the reminder that says, like I already told you out loud, you need to show me division. Okay? Okay, so we're going to do another one. The next one we're going to do has a little bit, maybe a little bit less friendly of numbers, I don't know, depending on your perspective, I suppose. We're going to do 99 divided into 29. So 99 clearly does not go into 29, so we have a 0, and we put a decimal point, move it up, and a 0 after. 99 will go into 290. How many times? 2. So what is 2 times 99?
198.
Yes, 198 and subtract. So what is 290 minus 198? It's kind of big.
92.
It's 92. So it's not as big as 99, but it's not far off of 99 either, right? Okay, so we're going to put another 0 up here and bring it down. Now we have 920. How many times will 99 go into 920?
9.
9. 9 times 99 is,
891.
yep, 891. And if we subtract, what do we get? Mm-hmm. Now, at that point, it's repeated. 29 is where we started. And let me tell you, if you don't notice it, it's okay. Just do another step or two, and you will very quickly find you're going to get a 2, and then you're going to get a 9. And you're going to be like, oh, look, now they're repeating. So you can always do more steps if you're just not quite comfortable with making that decision right away. But what I'd like for you to see is what happens is that since it repeats all the way back up to here, which is the point when I got the 2, right, that it's the 2 and the 9 this time that repeat, not just the 9. Right, I'm not getting 92, 92, 92, 92 as a remainder. I'm going to get a 29, and then I'm going to get a 92. Then I'm going to get a 29, and then a 92. The two numbers are repeating, both of them. So my decimal ends up being 29 hundredths, and the 29 hundredths both are repeating. So that part's usually something that feels very comfortable and familiar. It's the next part that's a little bit different. But it's very clever and it's very interesting. So in very much the same way that we would like to take a fraction and turn it into a repeating decimal, we'd like to take a repeating decimal and turn it back into a fraction. Okay? So pay careful attention, but we're going to do 3 of these, so it's not going to be just one. The process is the same every time. So we start out, we've got the number that's 61 hundredths, and the 61 repeats. So it's like 0.61, 0.61, 61, 61, 61 forevermore. Okay? So what we're going to do is we're going to set n, this is just an arbitrary letter, it doesn't even matter that I'm using an n, but we're just going to set it equal to the 0.61 with the repeating. And to be perfectly honest, it might actually be a little bit more helpful, instead of put the repeating, if you do a couple of them on here so you can see what's going to happen. You can even put sort of a ... at the end to remind yourself this keeps going. It'll just make it easier to see. Now, however many numbers repeat, right? In this case, that's how many numbers are repeating? 2. The 6 and the 1 repeat, so there's 2 numbers that keep repeating. What we do is we multiply both sides by the number 10, but it's however, like 10 or 100 or 1,000, it's however many zeros repeat. So I'm going to multiply by the number 100. Why am I multiplying by 100? Because there's 2 repeating decimals. So this is almost like what you were saying, Kessie, about the other problem from the homework. Can I multiply it by something big enough that I move the decimal over? And that's really what we're doing here. We're trying to move the decimal so that it gets past the first repeating. Well, if the decimal repeats twice, the only way I'm going to get it to go from here to here is by multiplying it by something with 2 zeros. So I multiply both sides by, in this case, 100, because 2 numbers repeat. So on the left, I get 100n. On the right, the 61 comes beforehand, and then I still have 6161 ... Okay, is that all right so far? Okay. So error number one people make is not remembering how many zeros to multiply by. A 1 with how many zeros? It's the same number of zeros as the repeat end. Remember the number of numbers in the repeat end. The second thing that people do is just simply not understand this next set. What we really want to do is we really don't want the 6-1 repeating part at the end to be there. We'd like it to go away. And here's how we can get it to go away. We can subtract the original 0.6161 that we started with. But notice that 6161 that we started with was equal to n. So if I subtract the 616161 on the left, I will subtract an n on the right. Because they're equal, right? One of the things you know about equations is that as long as you do something on the left-hand side that's equal to the right-hand side, it's the allowable option, right? Same thing here. The n on the left is equal to the 0.616161 on the right. Why am I wanting to subtract it that way? Well, because I have n's on the left and I have the 6 1s on the right. Okay? And here's the cool thing that happens. These pieces are all gone now, right? So I just have 61 on the left. On the right. What do I have on the left? Not 100, 99n. Yeah, 100n minus n would be 99n. And then what would I do to solve for n?
Divide by 99.
I would divide by 99. It is possible at this point that the 61 and the 99 are both divisible by something, and if they are, then we would do that. If you haven't had number theory, you may not remember how to decide if something's divisible. Obviously, you're looking for things that are even or multiples of 3, things like that. 99 is divisible by several things. It's divisible by 3, it's divisible by 9, and it's divisible by 11. Those are the 3 different numbers that you can kind of see quickly. The reason I know that it's divisible by 9 is probably obvious, and 11 is probably obvious. And you might be able to see that 61 doesn't match up with divisible by, at least by 9. You probably know your multiplication tables for 9s up to 61 maybe. And 11 is not going to work pretty quickly, right? It's not 61, it should be 66 if it were divisible by 11. The way that you can tell if it's divisible by 3, and this is true for 9s as well, is you add the digits together. Okay, so what is 6 plus 1? 7. Does 7 divide by 3? Then neither does 61. Does 6 plus 1, 7, divide by 9? Then neither does 61. But you can see that it will work on the bottom. 9 plus 9 is 18. Does 18 divide by 3?
Yes.
Then so does 99. Does 18 divide by 9?
Yes.
Then so does 99. Okay, so that's the trick for 3s and 9s. It's a clever one. We do it earlier on in this book, but we mention it now because it's helpful at the moment. So, yeah. So that means that this is prime. Not prime, but it's reduced. There's no way to simplify it any further, and we're done. Take a look at number 4 and tell me how it's different than number 3. Ooh, it's just the one that's repeating this time. Nothing else, right? Okay. Now, you start the same way, or write down n equals, but instead of writing down 0.616161, I'm going to write down 0.61111. I don't know how many ones you want, but put several there. And then put your dot, dot, dot. Is that okay so far? Okay. How many numbers repeat? 1. So we're going to multiply both sides by what?
10.
Just by 10, right? By a number that's 1 and 1 0. 1 0 because there's one number repeating. So on the left, I have 10n. On the right, when I multiply by 10, it moves the decimal 1 over. So now the decimal's moving over between the 6 and the 1. So now, after this, I just have 1s. However many you wish to write. Okay, so far so good? Okay, but I want those 1s to disappear, and it's going to feel a little bit less friendly than the last one, but it's not bad, just a little bit less. So again, I subtract n on the left. I'm always subtracting n, and I'm subtracting what n is equal to. So I have to actually look back at what n is equal to. It's a 6, 1, 1, 1, 1, 1. So I don't just decide I'm going to disappear the 1s. That's not what is going on. I have to subtract off the original n value, or the original decimal value. And I'll line them up. So this is 6, 1, 1, 1, 1. They all repeat, the 1s repeat, and those pieces go away. However, there is a 1 and a 6 here that does actually legit have to be subtracted. Okay? So when I subtract here, I have 9n on the left. What do I have on the right? What is 6.1 minus 0.6? You know it? 5.5. Good. It is 5.5. All right. And then what do we need to do? Divide by 9. It's very tempting to think we are done at this point. I mean, 5.5 and 9 don't have anything in common. But we're not actually done. And the reason we're not actually done is because if you remember over here, actually even in the directions it says on that screen we were on, it says it wants us to put it in the form of a over b, where a and b are integers. 5.5 is not an integer. It's a decimal. I need it to be an integer. So the quickest way to turn 5.5 into an integer is by simply moving this decimal one over. Well, that means multiplying by 10. Is that all right? So if I multiply by 10 on the top, what do we get? And on bottom? Okay, so now do 55 and 90 reduce? They do. What will they both divide by? 5. The trick for 5s is looking at the ending value, like evens, right? If it's divisible at the end, it's got a 5 or a 0, it will be divisible by 5. So we'll divide on top and bottom by 5. What's 55 divided by 5? And 90 divided by 5? 18. We check again, but 11 and 18 don't have anything in common, and so we're done. How could I check and make sure that I'm really right on either of these ones? What could I do? You could take the value at the end and just do the division, right? Grab your calculator. Take 11 divided by 18. Does it equal 0.61 with the 1 repeating? Yeah, so you should know you're right when you get to the end of these problems. And so if you're wrong, it means you made a mistake and you got to go back and find it. Okay, are you ready for your mind to be blown? Yeah, Addie is anyway. Okay, here's our third one. Same thing, it got a number that's repeating, so we set up n equal to 0.9 repeating. Now, instead of writing it that way, we'll write it with a bunch of 9s like we have been, right, with a dot, 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 so forth. Okay, so how many numbers repeat? 1. So what am I going to multiply by on both sides? 10. All right, so I've got 10 in on the left. What will I have on the right?
I have 9.9999.
Yep, the decimal moves 1 over, so I have 9.9 and a bunch of 9s. We'll put 4 from there for no particular reason. Okay, what's my next step? Not yet. Subtract n. Okay, so first we subtract n, and the value on the right-hand side that n is equal to is the 0.999's repeating. So 10n minus n is 9n. And 9.9999 repeating minus the 999 repeating gives me 9. Then what? What do you get? So later in the GC, you can tell somebody that you now know and can prove that these two values are equal to one another. Crazy, right? You're going to actually take a look at, though I'm not sure we'll get to it today, some group work problems that explore this idea a little further, this idea of repeating numbers coming from something that's terminating. Because like the number 1 is a terminating number, right? Totally is a terminating number. The 1 is, I mean, it's a whole number even. It's a natural number. It's like the first number children know, right? 1. And I can write it in this very strange form that says 0.9 repeating. And in some sense, that kind of shouldn't surprise us. We write the number 1 in all sorts of ways, right? 103 over 103, right? We do. We write the number 1 in lots of ways. But this is another way with repeating values that we can do that. Okay. It's so crazy, I know. Yeah. We can also find values that are between decimals. So we have this specific one that we just did, was 0.9 repeating, and 1.1. It says to find any value between them. So we could actually write out that 0.9 repeating is 1 and do this problem very directly. And that's fine. The reason I'm not going to do so, though, is because when you get to your homework, they're not going to use 0.9 repeating. They're going to use something else that's arbitrary. So I'm going to show you what to do when it's a general sense of doing that, or maybe sort of what you would have thought to do or thought made sense to do before you learned that 0.9 repeating was equal to 1. Okay? So if you're trying to find a decimal between two values, and it says any decimal, you just need anything. So this number you've got is approximately equal to 1. Okay? This number you have is equal to 1 point, and it might be easier to write it as 1, 0. All right, think in terms of money. So you've got the difference between like $1, even if you weren't sure that it was equal to, it's approximately equal to $1, and something that's equal to $1.10. What's any number between them? Okay, so $1 and 1 nickel, or 1.05 would work. What else would work? 1.03. Okay? And if you go outside of the concept of money, you can even do something like this. 1.04632. Right? Lots of decimals between these, no problem. Part B is a little bit more interesting if you were to find the decimal that's halfway between. So you can do the first one just by approximating without even knowing that the 0.9 repeating is equal to 1. It's almost equal to 1 in your mind, even if you're thinking about that, right? But if you're to find a number that's halfway in between, well, when we find something that's halfway between, so if you have two tests, one test is a 100 and one test is an 80. What's your test average? 90. Why? You add them up and divide by 2. So when you're trying to find something that's halfway, or the average of two values, you add them together and divide by 2. So truly, what we're doing is 0.9 repeating plus 1.1 divided by 2. But in general, you may not be able to think through or want to actually turn the 0.9 into the number that's, that it's going to be equal to, because you didn't just do this problem before, right? So pretend for a moment. So a really good way to sort of think through that and to use your calculator to help you is by using that decimal expansion out, 4 or 6 decimals, I don't know, something like that, and see what happens. So I'd like for you to grab your calculator, and I'd like for you to try adding those numbers together, 0.9 repeating for a few places. It doesn't have to be as many as mine, but something like that, and the 1.1. And I'd like to know what your calculator actually says. Like, what does it actually give you? 2.0. Oh, divide by 2, sorry. Do the next step, too. What? That doesn't sound quite right. Try again.
1.04.
Okay, 1.04995. Did that happen? So I want you to take whatever you did with your 9s and make them a few longer. Okay, so if you did 6 of them, do 7 of them now. If you did 4 of them, do 5 of them now. That part's going to stay the same. What happens, Kate?
The 9s increase in between.
Yeah, so the 5 at the end is because we're rounding.
Mm-hmm.
These 9s do start to repeat themselves, right?
So that kind of just rounds at the end,
Wherever it stops of your rounding that you did. So what happens is you have that 1.04, and then you have a 9 repeating at the end. It will repeat as well, okay? So the repeating ends, and it doesn't work with just 9s, it's going to work with 6s that are repeating or 4s that are repeating. The same process happens. It will be a repeating decimal that's halfway in between as well. Okay? All right, so here's what we're going to do. We have one more example today, which will finish us up pretty close to the end of class, or right at. And so what we'll do is we'll start 7.4 next time, but we'll do 7.3 group work in class as well. So this homework will push to the next day, so it won't be due until Friday. You're welcome to start it. In fact, I would encourage you to do so that you don't end up with things building up on yourself, but I won't collect it next time. Okay, so one more question before we end this section. You might be thinking, well, fractions and decimals, and there's some of them that just feel like, some people do anyway, I just like decimals. Decimals are so much easier to work with, okay? So this question kind of explores that idea. Some addition problems are easier to compute with fractions. It's true. And some are easier to compute with decimals. Also true. For example, 1/7 plus 5/7 is easy to compute. Agree? No problem. But if you had the decimal expansion for 1/7, it's actually equal to 0.14857 repeating. And the decimal expansion for 5/7 is 0.714285 repeating. Those are not friendly to calculate decimals with, right? I don't want to do that. But if you think about 0.4 and 0.25 added together, that one's easier in decimal form than the 2/5 and the 1/4 that are added together. It's maybe not quite as atrocious as the actual, like repeating decimal calculation, but it's still easier with the decimals. So what situations do you think it would be easier to work with fractions than decimals and vice versa? So let's ask the question. It's kind of a funny way to ask the question because it's asking it both positively and negatively and for both cases. So let's answer it like this. When do you think it's easier to work with fractions? When are fractions easy to work with? Maybe let's say it that way.
Maybe I think of graphing, like if you're taking like a statistic or something, and you have like a pie chart. Does that make sense?
I think it means the calculations we're doing here, like things
Okay.
we're adding and subtracting, those kinds of things, yeah.
Okay.
So when is it easy to add fractions? Y'all know the answer. Yeah. So when they have the same denominator. And maybe not even always the same denominator, but denominators that are easy to change into one another, right? Or same denominators are easily found. So I think that's a pretty fair statement. When is it easier to work with decimals? Or if you prefer, you can say, when is it not easy to work with fractions? When are decimals easy versus when are they not easy? What about these decimals made it hard? They're repeating. What's the opposite of a repeating decimal? Terminating. Yeah. So decimals that are terminating are easier to work with. Does that make sense? So in as much as you may have a, like a favorite option of which one you would normally do, there are still going to be cases where you're not going to like the way that you would do it in that situation. It just wouldn't be fun. And maybe not even just fun, but it would just be messy or ugly. And this is a really good example to sort of keep that in mind, is that decimals are not always better. I know my children seem to think that decimals are far superior and easier to work with. And in some cases they are. But some cases they're not either, especially when you're multiplying. Multiplying when you're working with fractions is sometimes easier than when you're working with decimals. So think about the multiplication one that you guys looked at. I know that the student made the error on the fraction one that we did from the homework last time. But the decimal expansion for multiplication and keeping all your decimal points lined up and everything as you multiply, it's kind of messy. It really is. Whereas if everything's written in fraction form, you just multiply across the top, you multiply across the bottom, and you're working with whole numbers usually. That's kind of nice. So there are cases when we would prefer to do one versus the other, depending on both the numbers we're used and maybe the operations that we're working with as well.